In previous lessons, we have reviewed surface currents. We have also reviewed groundwater. Now we're going to look at ocean currents. The ocean is a vast amount of water. If you've ever had the opportunity to go to the beach, for example, when you look out from the shore, you will see that there's no end to the ocean. Now keep in mind that about 75% of the world is covered in water. And the majority of that, of course, were going to be our oceans. Now, oceans are always in constant movement and is caused by two things. The first is variation in density and the second is wind. Specifically with variation in density, you have to keep in mind two things. First, let's make sure we know what density means. Now, I know currently there is a lot of things happening on the screen. I wanted you to be able to see them all at once, but I want you to focus at certain points. So I want you to focus right here, right now. It says, what is density? And it says density is a comparison of how much matter there is in a certain amount of space. And it tells us that mass is how much matter makes up an object, and volume is how much matter can fit in a place. So when we think about density, we want to think about how tightly matter is packed together. If something is packed very tightly together, it is considered to be dense. Looking at this seesaw, we have this cube is the same volume as the cube here on the right side. On the left side, we see that the matter is not tightly packed. Since the matter is not tightly packed, it is considered to have a low density. Here, we have where the matter is tightly packed together, and this is high density. So low density, less matter packed. High density has a higher amount of matter that's packed together. We will look further into the variations in density of ocean water. Looking though at the second one, which is wind. And wind, the primary focus of wind that we'll be looking at is the trade winds, and also wind taking the surface currents and moving those, that layer, I guess you say the top layer of the ocean, as part of it is the movement. But we're going to look at wind, the Coriolis effect, and trade winds are going to be our primaries. As we look at this is just explaining a property of water. And basically the bullet is what you need to know. It takes a lot of energy to heat up water, and it takes a lot of energy to cool water down. So that's one of the properties of water. And that's basically what we need to know from this slide. Looking at density currents, there are, this was one of our main differences. With density currents, there are two things to consider for density currents. That is temperature and salinity. Okay? So this is one of the reasons they call it the thermohaline current. So thermo meaning temperature, heat, specifically thinking about that one, and haline is looking at the salinity. As we think about how the temperature and salinity go hand in hand, I want you to think about tea. Okay? T-E-A-T. Some of us drink it, some of us don't, but still think about that. So in the South, we do not like unsweetened tea. Okay? It's not our thing. You got to have some sugar in that tea. So when you're thinking about this tea, I want you to think about hot tea and cold tea. So if you have a glass of iced tea and a cup of warm tea, and you wanted to put sugar in it, take a moment and think. What would it look like when you put a teaspoon of sugar in warm tea or hot tea versus when you put a teaspoon of sugar in cold tea? So take a moment and think about that. So as you thought about that, sugar and cold tea versus sugar and warm tea, you would note that granulated sugar dissolves slower in cold tea than it does in warm tea. And you'll also notice that when it's in the warm tea, it dissolves to a point to where you really can't see it. The crystals break down and it's all smooth in one thing. While the sugar in the tea, in the iced tea, stands out and you can still see some of it. Okay? So when we're thinking about warm currents, think about how that salinity, that salt, is all mixed in. And the cold water, not so much. Now next I want you to think about the conveyor belt. This is the global conveyor belt, the density currents. Now with the global conveyor belt, if you don't know what a conveyor belt is, you think you don't, but you actually do. Think about at Walmart, when you're scanning, or any grocery store, they have that belt that's automatic, that'll come right to where the cash register is, and then the cashier scans it. That's the symbol of a conveyor belt. So when we're looking at currents, we're looking at a global conveyor belt that is all around the world, okay, which is why we call it global conveyor belt. Okay. Now this conveyor belt's important for numerous reasons. The primary reason is as it cycles here, or actually throughout, you're getting that cold water. It's called upwelling when you have that cold water bringing nutrients up to the surface. So every time we have that cold water brings nutrients to organisms. So now we're going to look at the Coriolis effect. Now what the Coriolis effect is the rotation of Earth results in winds blowing in circular motion. The Coriolis effect makes things appear as if it's moving in a curved versus a straight line. Okay? The Coriolis effect affects weather patterns, it affects ocean currents, it affects air travel. It's pretty weird phenomenon, but the cause is simple. Different parts of the Earth move at different speeds. So the further you get from the equator, the difference you are going to travel. So remember, our equator is right here. You actually move faster here at the poles than you do at the equator. So because of this Coriolis effect, we call it deflect. Okay, so in the northern hemisphere where you are, objects deflect to the right in the northern hemisphere and they deflect to the left in the southern hemisphere. And we'll look a little bit at that more when we go into weather. The next thing that we want to look at is surface currents. These are currents that we mentioned earlier that affect the uppermost portion of the surface of the ocean. So you have different layers to the ocean. So this is that top layer. The primary thing that you need to know is where the oceans flow from, or where these currents come from. There's temperature changes. So for example, imagine this is the equator. As best that I can draw an equator right now. Actually, I'm going to try to be fancy for a second, guys, and see if I cannot draw an equator. And I cannot. So, well, that went. But here we go. Anyway, this will be our equator, our pretend equator. If it is, and I accidentally changed it. There we go. In our pretend equator, if it is flowing from the equator, it's warm. Because remember, your poles are colder areas, so your north and your south pole are colder areas. Your equator is where it's warmer. So if it is flowing from the equator, it is going to be warmer. If it's flowing from the poles, it is going to be colder. Okay? I'm going to get rid of this pointer for a second because it's driving me crazy. Sorry. Okay? Again, equator, warm arrows. Notice that when it comes from the equator down, or in this case up in the northern hemisphere, down in the southern hemisphere, if it's moving from the equator, you see the red arrows. If it's going toward the equator, that means that it is colder. So it has come from these pole areas. That's your primary thing you need to know about your surface currents. This is another good shot right here that shows your patterns. So as it flows from the area to the area. When it comes to climate impact, I want you to remember what we spoke about earlier, that there's a specific, water has that specific heat index. It takes a lot of energy to cool it, takes a lot of energy to heat it. When it comes to coastal areas have a high amount of water vapor. Water vapor is just the gas form of water. It's called water vapor. Okay? This means the summers will be cooler and the winters will be warmer. So what happens is the water in the ocean Now I need you to remember as we move on the climate impact, the property of water from, I believe it was like the second slide, which means that water heats faster, or it takes light energy to heat water, takes light energy to cool water down. So we're going to look at two areas when it comes to climate impact. We're going to look at coastal areas and inland areas. And it says coastal areas have a high amount of water vapor in the air. And water vapor is just a gas form of water. Remember, water can be found in all three states, solid, liquid, and gas. So you're looking at the gas form of water. In the coastal areas, summer will be cooler, winters will be warmer. Now, why is that? The water in the ocean heats and cools at a very slow rate. The ocean stores heat in the summer and releases it in the winter, and then it starts the cycle all over again. So as a result of this cycle, winters along the coast tend to be warmer than winters inland, and summers along the coast tend to be cooler than summers inland. Another thing to remember specific to North Carolina is during the summer you have the sea breeze. And the sea breezes are stronger than they are in the winter because of the large temperature differences between land and ocean water that time of year. Okay? So, excuse me. When you're looking for the climate inland, so we just looked at the oceans. When you look at it inland, which is also on land, is what we're referring to. It says cities located further from the coast, there's less water vapor in the air. And because of that less water vapor, summers will be very hot and winters will be very cold. So even though your land heats up quicker than your ocean, the issue becomes that it also loses that heat at a faster pace as well. So those winters are very cold because that heat it's lost its stored heat from the summer. It's gone. All right, ladies and gentlemen, that is the end of our segment. Please check Google Classroom to answer your questions.